Okay, we're 2 minutes past time, so let's get started. Today's first talk is coming from Weixiang in Drexel, and he's going to be talking about building the Asian data science data challenge dataset. Weixiang, if you want to get started. I think you're muted, Weixiang.
I guess I just muted myself. So, okay. Yeah, this is Weixiang. I'm a final year PhD student working with exploratories at Drexel. Today, I will talk about building a comprehensive data set in preparation for LSST agent science. And the early version of it that was used to run the data challenge also provide some updates to the data challenge.
Yeah, Weixiang, sorry to interrupt. Your microphone is coming across quite crackly. I don't know if there's another mic you could use or any way you could try and clean up the audio.
Oh, sorry. So how about now?
That's much better, thank you.
Okay. All right. Let me get started. So what do I mean by a comprehensive data set? I think it should cover some basic characteristics that are listed here. Should cover a pretty dynamic range in the data, a wide range of the electromagnetic spectrum, sources including the data set.
Weixiang, still bad, I think.
Still bad?
Yeah.
I think when you hold it up to your mouth, it's better, but when you let it go, it gets worse.
What about now?
That seems fine to me.
It's not the volume so much, but I mean, we'll just have to do the best we can.
You disappeared completely now.
What's that?
You had disappeared completely.
Just give me 1 second. Sorry about that. Thought it was.
Now you sound very good. So just keep it like that.
Oh, now it's good?
Yeah, now you sound very good.
Okay, perfect. Yeah, it was just that special spot didn't work well. Okay, where was I? I think the data set should be include objects from various different classes. Most importantly, need to mimic the multifaceted nature of LSST data. That is, in addition to photometry, need to include astrometric information like popular motion, parallax, and variability data. That is light curves, right? And some level of truth need to provide it for at least a pretty good portion of the sources in the data sets. The data challenge data sets was actually our initial attempt to construct such a data set and to make it available to the community for testing. To refresh your mind, Agent Data Challenge was initiated to motivate planning and preparatory work for LSST agent science with some focus on 3 main areas: parameter registration of agent light curves, agent classification, and photo Z estimation. I would like to give a shout out to those who have co-signed this proposal. Without your support, Agent Data Challenge wouldn't have existed. So the data sets we put together include sources from 3 main classes: stars, galaxies, QSOs, or AGNs, from 2 main survey areas. One is the Stability 2. We extended a little bit to a larger area to maximize overlap with other surveys. So that is shown in blue. Also the XMM LSSS area, that is shown in red. For half of the sources, we include the light curves from the SDSS Rep 82 survey. Later on, we added image cutout for nearly all of the all of the sources as requested by the Italian team. So here is a list of the different public service that we are taking our data from to compile the data challenge data sets. The data categories that are shown in blue makes the our data sets give the data set the multifaceted nature, and the truth table come from the spectroscopy that's shown in red. Given the light curves, we computed roughly 320 time series features in two main categories. The first one is periodic features, which include Karma-21 and Dem harmonic oscillator, DHO fits, and generalized Lambda-Gargoyle fits from the Richards 2011 paper. To note that this is not our own Richards. And another category is non-periodic or aperiodic features, mostly those from the same Richards 2011 paper, and a selection of them from the FAST library, also fitted light curves to the Karma-10 or DRW process. Here I'm showing the distribution of three selected variability metrics of galaxy, star, and QSO. We can already see from the distribution that variability will play a very critical role in selecting AGNs and separating different sources for LSST. Okay, a very brief summary of the submissions to the data challenge. The submitted solutions cover a wide range of algorithms and techniques ranging from random forest, convolutional neural networks, autoencoders, and also transfer learning. Both supervised and unsupervised algorithms are seen in the solutions. Some run on catalog tables, some run on image cutouts, some trying to combine both to maximize the information they can utilize. Pretty high classification accuracy was achieved by several of the submissions on the DC data sets, but I like to stress that this very likely wouldn't be the case for LSC data sets for many reasons. One of them is that we test the DC data set was constructed from all spectroscopically confirmed sources. There are some built-in bias in the distribution of different sources, different classes. And for LST, we're going to see much deeper than the sources that are currently included in DC dataset. So please see George's talk for more details on the different submissions to the data challenge. However, I would like to highlight one solution that I found really interesting. That's from Wisinto. So he basically exploited the correlated AGN variability across photometric bands. So in this plot, I can see that the R band magnitude and G band magnitude are correlated across time. So he computed a correlation coefficient for all sources using the light curves included. And here in the distribution, you can already see that quasar and galaxies can be separated using this statistics. This final solution included other information like color and morphology. Just use those very simple statistics. He was able to achieve a pretty high completeness and purity. Now are some updates to the data challenge data sets. We finally made it public available on Zenodo. A slightly updated version also made public. We disclosed the true coordinates at extinction for every object using the SFD 1998 dust map. Included also the spectral information from SDSS if they're available. Worth noting that we're still accepting contributions and submissions. Given that we have disclosed the true coordinates, so you can start to contributing data sets in addition to algorithms. Okay, so next I want to talk about is how this data sets can still be useful for facilitating algorithm development, testing science ideas in preparation for LSST. First, I'm going to simply talking about our recent work of modeling SDSS A2 QSO light curves as DHOs. So basically, DHO, or the full name is Dem harmonic oscillator process, can be described by the differential equation that is shown at the top. Thinking that we have a perturbation response dynamical system, the left-hand equation tells you how the dynamical system would respond to a delta function perturbation. And the right-hand side of the equation describes the actual perturbation put into the dynamical system. The initial motivation behind using DHO to model AGN and light curves was that the power spectroscopy of DHO can take more flexible shapes than that of a DRW model. Where on the left, you can see the power spectrum density of a DRW model follows a fixed shape, which has a slope of -2. And that of a DHO can go steeper than that. The flexibility directly resolves the discrepancy between a DRW description of AGN variability and the observed steeper slope of Kepler AGN light curves at higher frequency. I'd like to note one interesting observation that we have made by this modeling work. That is, we find the perturbation parameters that was used in the right-hand side of the differential equation follows Vulcan parallel relationship with terrestrial wavelengths, with the breaks occurs at roughly 2,500 angstrom. So that indicates that the quasars that are best fit by this DHO model might have a two-component accretion disk. So the right-hand side figure gives a schematic view of such an two-component accretion disk. So from ISCO to the inner edge of the truncated disk sits the Hall X-ray corona, and from inner edge to some intermediate radius, there's a the inner accretion disk. Well, the thin accretion disk is sandwiched by warm electrons in the atmosphere. We call this a worm compensation region, and from our worm to the outer edge of the disk, it is just a standard thin accretion disk, which is here we're showing in purple. And in this picture, the purple region is at the direct illumination of the X-ray photons coming from the corona. However, the green region, which is a worm compensation region, the high energy X-ray photons will be scattered, diluted before they're reaching the inner accretion disk in the center. So that gives the different wavelength dependence, the two perturbation parameters, than that of the bare standard accretion disk. So I'm noting that the parameters that we're using for the study is actually provided in the data sets. Here it shows how you may get those parameters. There are more details described in this paper that's currently being accepted for FJ. So if you're interested, please have a look. Another example I'm showing is a very basic experiments that I did to simply satisfy my curiosity. We all know that obscure quasars are important to study for the evolution of quasars, etc. I have always wondered if there are any additional information from variability that I can utilize to improve the selection of obscure quasars. So I made some simple tests using the data challenge data sets. I excluded those that at high has high galactic extinction, and plotted the G-R color. You can see that there is some objects that has excess color, and then I did some exploration, basically looking for correlations between the G-R color and the variability metrics that we computed, and we did find something that's very interesting. So here on the X shows the G-R color, and on Y-axis shows the LC non-parametric 22 metric in G-band. You can see that those objects have excess color tend to have lower value of this metric. So the color shows the U-band photometry. So if basically we can just select those objects with this excess color using U-band magnitude and this variability metric. And then I further wondered, can we can we just select those using variability information alone without the photometry? And yes, apparently here it sees that you can see that there's two plots shown. The objects with excess color are located in a very sort of a low outlier region in the variability perimeter space, which means that you can probably use just variability information determined from different imaging light curves to select those obscured, potentially obscured quasars if the color is a good proxy for that. So the point of showing this experiment is not to say that I use an afternoon to develop a new selection algorithm for obscure quasar, but to say that actually the data challenge datasets is still very useful for testing new ideas, developing new algorithms, facing the upcoming LSST operation, especially taking most advantage of the multifaceted nature of LSST data.
3 minutes.
Was that?
3 minutes.
Okay, cool. Yeah, so what's next? Presumably we can have some founding, then there's a lot of things we can do to extend data sets, including more data sets that have just been mostly recently made publicly available, also deeper data from HSC. Also, I will note that the Delcast and clouds, the clouds is the U-band survey matching the depths of HSC to roughly AB of 27 in the deep and ultra deep HSC fields. Most importantly, I want to say is we need to add different imaging light curves from both real light images and simulated images. Additionally, simulated data like those coming from the Italian team through in-kind contribution will be really valuable. Next, I would like to draw everybody to the challenge and the lack of computing infrastructure again. I know that has been discussed in the previous 2 days. So we basically need a central place to share our data and run our codes, especially given that now we have income contribution coming in. That's, we need that infrastructure to collaborate. Site server is a good starting point, but it's very limited in capability. There are some free solutions. First will be the federal funded high performance computing facilities. Basically, we can write grant proposals to try to get time on those, probably Link or other in-kind contribution data facilities, but I don't know if they are designed to do that. And there are also paid solutions, Google Cloud, Amazon, AWS. I'd like to stress that even though we might find some temporary solutions right now, when the data actually flows in, the amount of work we're trying to do wouldn't be supported by the free LSST computing given by the project. So for example, we want to run our own agent classification algorithm, compute photos, also monitoring a watch list, probably on the level of millions of agents that won't trigger alerts. So I would like to say that we should certainly start thinking about our own computing dedicated infrastructure right now. Here, just a summary. In the next steps, I have included the link white paper for reference. There's a lot of things that are doing is overlap with what we're trying to do through the agent data challenge, and also what I've been doing to build agent challenge data sets. So there is working collaborations between us and their efforts. Yeah, thanks. That's all I have. Happy to take questions.
Thank you very much, Weixiang. And it's great to see all the science that will be possible with the data challenge data set. Just as a reminder, if people want to ask questions, feel free to either raise your hand or put them in the Zoom chat. If you've got discussions you think might be worthwhile for longer term thoughts, then you can always put those in the Slack channel as well, AGNSC-2022. I see we already have a question from Bijana. Bijana, do you want to unmute yourself?
Yes, I have a question about this other variability model which you are using instead of dumped random walk. I'm not really familiar with that model, but it lets you, at least on this plot, to something which is really unphysical, because if you look at the observed power spectrum of an AGN, going from the highest frequencies, it is first steep, indeed much steeper than damped random walk, and then flattens to -1, and then flattens to 0. But it never goes like that, flatter and then steeper and that flatter. That simply does not happen. So I'm not sure if it is an unfortunate example or just generically this DHO is producing strange results.
So, yeah, it's a good question. So this is only the showing is a PSD of one realization of a DHO process. It can take many different shapes. Probably that's the particular example I have chosen that has given you an impression that this is not, physical. Does it answer your question?
Okay, if it can give better shapes, then fine.
Yeah, DHO is very flexible in terms of the PSD shapes. It can also mimic the shape of DRW.
Yeah, that is simple, but can it mimic this situation steep, moderately steep, and then flat?
Yes.
Because this is how power spectrum looks like in AGN.
You mean like a more not this deep, not -4, but like -3?
Yes,
right?
like something like starting with -4 and then -1 and then 0, more or less.
Yes.
Okay.
Yeah.
So I will read more on
Thanks,
that.
Virginia. We also have a question in the chat from JT Schindler. Hey, Weixiang, thank you for the great talk. Over what redshift range do you do your obscured quasar selection exploration? And related to this, how does the redshift dependence influence the color and variability signals? Questions in the chat if you want. I think basically is, for your obscured quasar selection, what redshifts do you use, and is there a color variation as a function of redshift that could be?
Yeah, so the first I made a cut on redshift. So it's really naive and simple test case. I want the G and R band to be on the continuum, so the emission line doesn't play a big role. Also, I limited the magnitude to range because we know the variability is correlated with the luminosity. I don't want that to play a role either. So I did some cuts to isolate other varying factors in there. But again, this is not, a science showcase, but rather you can say that you can do different explorations based on your taste.
Yeah, understood. Right. We should probably move on. So thank you very much, Weixiang. If anyone has any further questions for Weixiang, feel free to either ask them in Slack or in the chat. And if you can stop sharing, Weixiang, and George, can you share your screen?
Thank you.
All right, it should be good now.
Yeah, and I can see a video, but it's quite orange. I don't know if you're...
Just a second.
So our next talk is following nicely on. George Savic from Serbian Collaboration Group is going to be talking about the results from the data challenge and some of the outputs from the algorithm development. So George, when you're ready.
Yeah, I'll be in a second. All right, should be good now. So we continue with the LSST AGN data challenge talk. Weixiang made a great introduction.
George,
and
sorry, can you make your slides full screen?
Are they?
No, we can see the panel down the left with all the slides, and we can't see the presenter mode.
No. let me see, for me is a full mode.
That's better. Thank you.
Okay. So yes, currently I'm a postdoc at the University of Liege in Belgium, but a member of the CERSAT team and of course the LSST AGN science collaboration. So we continue with the data challenge hosted by the AGN science collaboration and with the idea of developing machine learning methods for AGN science with LSST. So the idea is simply to get prepared and get started. And there were three main goals to be challenges to be addressed, or problems. The first one, the AGN classification, measured as both by completeness and efficiency, photometric redshift estimates, as well as the light curve parameterization. And of course, the final category were some other results that were not otherwise specified, but basically any other contribution to the data challenge. I mean, there were in total 5 submissions, and all of the teams were dealing with the AGN classification. So that's going to be the main problem here that we are working on. So as we know, that's the AGN selection, or the star galaxy classification, is the fundamental problem in astronomy, dating from many decades ago. And there have been different methods or ways of dealing with this. The most commonly used, or the most widely used, was the color diagram selection, because it is known that quasars, galaxies and stars populate different regions in the color diagram, but also there are some overlapping regions as well. Also, some of the method that was used was the fact that quasars lack proper motion, so that has been used as well. Also, recently, variability has been added, and we know that variability alone can also be used for AGN selection. And now, more recently, we start to put simply to merge many of these methods into, or ways of selecting AGNs into some more advanced algorithms. So, for example, even more recently, colors plus variability for luminous AGNs have shown promise, and also recently images have been added to the classification, particularly for training convolutional neural networks that would decide based on morphology. So that's what we are going to do here. And as Weixiang described, the dataset basically pulled from mainly from the Stripe 82 region for the extended, with the addition of the XMM LSS field. And in total, we have around 400,000 objects, roughly of which 400 is just with known labels. The data set itself is grouped, when it comes to data features, is grouped into 7 categories. So with the astrometry, so we have the positions, but also we have the proper motion that will also be used, the photometry measurements, also colors that were computed. There are some morphology parameters. So 1 is for extended sources and 0 is for point-like sources. There have been a large amount, but I'll explain it later, of a light curves feature that were computed for the SDSS light curves. Also, redshift is given if known, and most reliably the spectroscopic. And of course, we have the class labels. In total, that's around that's 381 features in total. So an important part is the addition of time series. So basically, we have raw light curves here in the 5 bands, so U, G, R, E, and Z. And also there have been a number of parameters that were engineered from the raw light curves, simply because the number of visits, basically we have light curves with roughly between the highest number of light curves are having the number of visits between 30 and 70. There is also a little bit of highly sampled light curves, but overall, let's say 50 points is just fine, and that's not enough for putting incorporating in the model some more advanced techniques that therefore we rely on simply on time domain features that we extract. In addition, we also have some image cutouts that are 64 times 64 square pixels in the three colors U minus G, G minus R, and R minus I. And there have been a couple of attempts to use those images as well to improve the classification. The machine learning methods that we use, so we basically tested many of those, both supervised and unsupervised methods. For supervised and for supervised methods for classification, we use the standard support vector machines, random forest, and extreme gradient boosting as bagging methods. We also gave it a try with the artificial neural networks as well. And also there have been a couple of attempts with unsupervised learning, whether if it's for dimensionality reduction, the autoencoder, even the PCA methods, also T-distributed stochastic neighbor embedding, or T-SNE. And we also attempted some locally linear embedding for dimensionality reduction. But in any case, there will be no, up to now, there is like no definite way of solving this problem, since methods mostly converge to a very high accuracy. And it is also possible to combine many of these together. Like, for example, simply we use the dimensionality reduction, and then we for reducing the latent feature, and then we simply apply on the latent features some of these methods. This also works more or less fine. We also did some pre-processing, because some of the method lists here requires the data to be standardized or pre-processed, and for that we simply did some cleaning up, removing all the objects with none values, and also we found some nice features that could be used for doing the classification. And we can see, for example, here, this is one of the engineered feature for the from light curves. We can see here in blue, for example, quasars have been populating, it's possible simply to separate largely quasars from stars and from AGNs. Also, morphology is very good for separating galaxies from quasars and from stars. So that would be our major thing. We did the standard train test validation split. This is the ratio, so 0.7 for the training, 0.2 for the validation, and 0.1 for the test set. And we also there was additional blinded data set that was used, that was later revealed to make it like a proper data challenge. And of course, we after that just standardized all of our features for the train set, and then based on those we scaled the features in the other three remaining data sets. And after that, we are ready with for applying and playing with the machine learning models. We had one simple attempt by Vincenzo, who did like explicit selection. So the idea was to use the time series in a simplest way. So basically computing the correlation between the different bands between the light curves, and to use the magnitude deviation. And as seen here, like this this wedge here is simply able to select AGNs with 95% of purity. So when we look at this diagram, this is wedge, so wedge data points are transferred here. There is also some missing with stars, but galaxies are simply excluded by using the extendedness or the morphology parameter setting, for example, threshold all objects with extendedness parameter higher than 0.95 were excluded, and that excludes a large amount of galaxies, and we end up with a good purity, and completeness is around 85%. After that, we were just training our methods, and I'm going to show here the results for the blinded data set and for the test data as subsets. So we were able to achieve 98% of accuracy for all the methods. Basically, they only make a difference at the third decimal point. So the artificial neural network support vector machine, extreme gradient boosting, this one gave the best results, and random forests. So what I can say for sure after testing many of these methods is that on the data set that we used is that stars can be very well isolated from jointly from galaxies and quasars. And yeah, so that's like when we convert this into a binary classification, whether an object is a star or galaxy plus QSO, we reach almost 99% of accuracy for the binary classifications. And yeah, these methods have all of these tests can be done even on a single computer. You just need like 16 GB of RAM memory, and it should work. So yes, just using the tabular data with the features previously selected, we got a high accuracy. There was also one experiment that Weixiang did, was simply instead of using the engineered features, he used the so-called density maps. So the idea is to, with this, is to code the light curves, raw light curves into images. That is basically 2D images with the change in magnitude and the change in time space. And we obtain images like this for example, galaxies and stars look more or less similar, but quasars show different images. And we use those to train convolutional neural networks. And this is one example here as was used. On the right side is just the branch that was used with tabular data, but only including magnitude. So everything except for the time series. And on the left branch, we just simply merge the convolutional neural network for training on images like this. And this one works slightly less than 98%, but is more robust in a sense that like the same accuracy has been obtained both for the test and the blinded data. So it's a bit more robust. It doesn't use the engineered features, but you code. So basically, so we could say that our new time domain features are just images that are used for convolutional neural networks to be fed, and it works good. Also, one attempt was done to use like the fully unsupervised learning for clustering and see whether we can get how far we can reach with the unsupervised way. And so this is all again for the tabular data with including time domain features. And the method is called deep embedding clustering. So it combines the autoencoder for the dimensionality reduction and the t-distributed stochastic neighbor embedding for doing the clustering. And basically that's it. So we at the same time during training we minimize the mean square error for the reconstruction error for the autoencoder, while for the clustering we use we minimize the Kalbach-Libler divergence with the help of t-distributed stochastic neighbor embedding. And for the test data, it was able to achieve accuracy a bit higher than 90%, 97%, and is by 1 or 2% lower than on the blinded data set than the supervised method, which is personally for me like a very good result, as we are simply able to select to differentiate with high accuracy what's a star, what's the galaxy, and what's the quasar, even by not knowing any of the labels. Yeah, the next part was to do the locally linear embedding, and it's another method for doing dimensionality reduction. So basically, it's one of those that preserves the topology of the input space. It relies on computing the reliability score, after which we simply set up manually what is the reliability score for removing outliers. And then after removing the outliers, we train our classification method. And with outliers, this brings 98% of accuracy. And when we remove them, it's possible to by 0.05 it's possible to by 0.5%. It's possible to increase the accuracy with this method. And just the main comment for this is that it doesn't similar method. If you want to use the autoencoder for this, it doesn't work, but it works with locally linear embedding. The next part was simply to use the addition of images. So here we can see here, these are the actual 64 times 64 pixels, but these are just like point-like sources with the images with basically very few number of objects have any morphology traits that can be used. And the only good thing that we were able to pull out with images like this was to simply for some when there was autoencoder training, but using images, it doesn't improve any images of this quality doesn't improve any accuracy for the classification. Now, one of very interesting results for which the paper has been submitted by Lars Dorenbos. They used a pre-trained network on ImageNet, and they feed Galaxy AGNs, for example, like this, and then they compute the k nearest neighbor of objects to the latent features, and this is what we get. These are the 25 nearest neighbors, and when you look, you set up also some threshold that is distance to the query for this, and if you select all objects that have less threshold than this, you simply get, I don't know, in this case is like around 50% of neighbor objects that were included are AGNs. And for summary, basically, so we started with the LSST-like data that were pulled from different archives. We trained different versions of machine learning classifiers by achieving very high accuracy. We know for sure that they have shown that images with higher quality is definitely required in order to utilize the convolutional neural networks. There will be two. One paper has been submitted. The other one will be submitted soon. And the final remarks is that All the notebooks will be publicly available, and they were written as an end-to-end examples. So yes, for those who haven't checked, check the website on GitHub and on the LSST Science Collaboration for this for the AGN Data Challenge.
Thank you very much, Giorgio. What questions do we have? Gordon?
Thanks, Georgia, to you and Weixiang for putting this nice summary together. Just really quick, I want to say, while there was no funding to support the construction of this, we do have a tiny amount of money still left from LSSTC for participation awards. So something like a dozen awards of like $250 we can distribute. And if I don't distribute that by the end of like September, I'm going to have to give that back to LSSTC. And then, so second thing, will you go back to slide 20? So this isn't a comment for you or a question so much as just a general comment for everybody, you know, since we've talked about this. If I had to bet, something like this is what our final structure of our algorithm is going to look like. It's going to have other things layered in, you know, putting in images, putting in, you know, the periodicity metrics, putting in the correlated band, you know, things, you know, something like that. So, you know, I just want to throw that out to people, right? I think this is sort of the thing that we should be, the structure we should sort of be thinking of. I think the accuracy is sort of misleading, as Weixiang said, because, you know, the data is a little biased. And that also means the 1 or 2% lower accuracy, I think we shouldn't be distracted by, right? If you had a real, truly blind data set, I think you might find something like this, you know, works pretty well. That's all.
Thanks, Gordon. I'm not sure if there's a question there for Giorgio to comment on, but maybe I can ask a quick question, which is, you know, you had 3 labels. You got, you know, QSA, Star, and Galaxy. Have you thought at all about what will happen if you want to be looking for things like low luminosity AGN or CFIT-like galaxies, where you've got sort of a blend of Galaxy and AGN, especially as you start going to fainter magnitudes?
Yes, and for that I can definitely say to give a look for the in the paper by Lars. They have shown that this will particularly work nicely for the low. This approach is very promising for the low luminosity AGNs with images, so they will come there pretty much handy.
Okay. All right. Well, thank you very much. Quick question from Maurizio then. Perhaps Filippo can start getting his slides ready while Maurizio asks his question.
Yes, it's more of a comment in saying that just to remind that Demetra showed in last year meeting also some attempt to retrieve lower luminosity AGN using different data set, the one in the Cosmos field. So in that case, her publication showed the efficiency, although those were not machine learning, but she added a recent paper using machine learning. So this, when in the data challenge, was a bit hard to cover that range of luminosity because how the data challenge was produced and because there wasn't enough X-ray coverage to find the truth table of object, but has been done with other data sets.
Great, thank you. Okay, so our next talk is from Filippo Domando, who's going to be talking about synergies with CTA. Filippo, I can see your slides, but they're not in full screen mode.
You don't see in full screen?
No, I can still see the sidebar on the left. And
okay. Let me try again. So now you can see better.
No, you might have to stop sharing and
okay.
try restarting your screen share.
I can try again. don't think it's bad. Let me know.
Okay, I mean, I think it'll be good enough. They're pretty big, so when you're ready, if you want to get started.
I tried last time just to be sure, but it's okay. Try to share this different screen, but no, it's stuck on the not on the full screen. I don't know why. Sorry for that.
Okay, we can still see everything. So
this time I will try to make a first exercise that we have already done for the CTA Observatory. So what can be the synergy between LSST and the CTA for the study of the physics of relativity? This is something that probably will be done and should be done for other facilities. First of all, something that you have already seen, but I want to underline more time, is that at the moment, for the blazars within LSST, there was a lot of efforts by Claudia Recari that lead the main work and the main publication on blazars. And you can see here the two main publications. It's important to stress that without the effort by Claudia, probably most of the ideas that are inside this presentation will not be there. So I think that we will live in a new golden age of astronomy. And here you can see just a small selection of large facilities that in the near future or currently will be available for us, from SKA to the radio to CTA at the very energy. And it's important for these facilities and for the scientists that want to use these facilities to maximize the scientific return from the observation. And this can be done only from a combination of data at different wavelengths. Because if you take a look at something at a one frequency or another, it's not completely clear to you what you are giving a look. So you need to start to have a better picture, and only a combination of images of data at all wavelengths can make the pattern more clear. So this is an important exercise that we should do as LST, but also, of course, as CTA and other collaboration. So just a few words about the Charikov Telescope Array. That is a facility for very energy gamma astrophysics in the next decades, with the two arrays, one in the north and one in the south hemisphere at La Palma and the Paranal, just 10 kilometers from the ESO, with different classes of telescopes. And here you can see the design of these telescopes that are divided in small size, medium size, and large size telescopes with different energy coverage for a overall coverage of the energy spectrum from about 20 GeV up to 300 TeV. And the initial configuration of the CT array, that's called the alpha configuration. So this is the configuration that we have at the beginning. The final goal is to have the omega configuration, but I will discuss only this. Is includes 4 large telescopes in the north and 9 medium telescopes. And the northern array will be focused mainly on extragalactic science, while the southern array will be focused on galactic science. Of course, this is not so good for LST because the overlap is not so large between the northern array and the southern array, but this is something that in principle, going ahead with the different configuration for CTA also the southern array can be more related to extragalactic science in the near future. And just to provide you a couple of plots on the left, you can see the sensitivity curve of the two southern and northern array with respect to the current Chile telescope, Veritas, Magic, with the same with the same amount of time, so 50 hours of observation. And here you can see also with Zwigo and LISO, but with a longer exposure time, so 1 year and 5 years. And another important strong point for CTA will be the possibility to have great sensitivity at shorter time scale, also with respect to the Fermi-Lat. CTA will cover a large amount of science team and with different capabilities that will be improved with respect to the current generation. Here you can see just a combination of all what will be the improvement, and the consortium, the CTA consortium, will have some key science projects. Among the key science projects, there are one key science project on AGN and another on extragalactic side, in which most of the sources will be the AGN. And here you can see a link to the science book of CTA. Going more in detail in the CTA AGN key science project, this key science project includes 3 classes of observation. So long-term high cadence monitoring of a sample of AGN for 10 years, the search and follow-up of AGN flares based or on external TO, as can be observation from LSST, or internal snapshot monitoring of a large number of AGN. And there will be a number of sources for which high-quality spectra will be provided for different coverage of redshift AGN topology. As I said, there will be also the extragalactic survey during the first 2 years of operation. So what can be the synergies with LSST? Starting from just from the 3 classes of observation of the CTA key science project, contemporaneous, at least contemporaneous slab curve at different wavelengths are needed to allow us to search for correlation in time lags between different bands. And this is something that in principle can be a first point of synergy with LST for the follow-up of AGN flares. Of course, multivariate coverage is crucial for variability studies and in dynamic spectral modeling of Penn states. And for in case of high quality spectra, it's not important the simultaneous observations, but it's important to have in a contemporaneous epoch some data. And for the extragalactic survey, the characterization of the properties of the very energy detected AGN can be obtained also using the LSST data. But let's see some example. Let's see something more related to physics that we already done. This is an example of a flash spectral quasar observed at very energy by Magic with the collection of light at a different frequency and SCD at different epochs. So what we can do, combining the observation of CTA with LSST, can be searching for correlation and time lags and build up SCD variability. So this will be important to have information on the emission processes at work in the jet and the location of the meteor region inside the jet. What can be the warning point for LSST? Of course, the cadence of the observation and the time separation between observation and different filters are important. In particular, if you want to collect SCD data over a wide range of frequencies. So this is something, of course, that cannot be obtained for all sources, but at least for some of them, hopefully we can have. And the long monitoring, the continuous mapping of the sky of LSST can be even more important for the AGN that are related to the emission of high-energy astrophysical neutrinos. This is the first example of an association, the famous TXS0506. And here you can see another collection of light curves from the very energy with magic up to radio with optical light curves here. Because it's important not only to see what happens at the time of the neutrino, but have a long-term light curve with at different times. So before, during, and after the neutrino detection can be important to be compared with the prediction of the theoretical framework in which neutrinos produce in the blazar jet can be. Another warning that can be important for LSST is, of course, the saturation, because for the brightest blazar, saturation in LSST can be a problem, and so this is something that can affect some of the potential sources of high-energy neutrinos. But in principle, the possibility to have a long-term light curve for 10 years of candidate AGN neutrino emitters is very important in the future for a connection also with the CTA, and this can be also useful for searching for AGN periodicity and for blazar. This is something that has been done at the moment only at high energy with the Fermi Gamma Ray telescope. Here you can see a light curve at different energy with the Fermi-LAT. And some hint has been observed also in optical and partially in radio and X-ray. So the possibility to have a statistical study of long-term variability can be very important, searching for signature of periodicity and a signature of potential binary record system, with implication also for gravitational wave astronomy. So this is another strong synergy in the future, because likely with CTA, at least for some sources, we'll be able to have a long-term light curve also at very energy to be compared with the optical light curve collected by LSST. And of course, the hours obtained by the brokers, the Rubin LSST from data products delivered by brokers will be important for follow-up with the CTA. Currently, optical telescopes have provided for current very energy telescope alerts that lead to the detection of very energy. This will be even more important in the LSST era. Of course, it's important to have suitable filters for selecting effectively blazars. We have seen a great talk by George about this, but the diagnostic methods based only on variability colors seems to be not enough from some studies that we have done to separate quasar from blazar. So this is important if you want to follow up blazar sources instead of AGN in general. And of course, if you already know what are the targets that you want to follow up, saturation is not a problem, because you can provide a list of sources, and when there is a rising trend, you can start to think if follow or not. But for new flaring very energy blazar, saturation can be a problem. The last possible science team that can be a synergy, it's something more related to LST. It's not time constraint. It's the study of the environment of the blazar galaxy, collecting year and year of data with LSST, and so the possibility to compare the environment of blazar radio galaxies with LSST Rubin can be important to confirm or not if radio galaxy that should be the parent population blazar and share the same clustering properties. And from estimation done in the paper by Claudio in 2018, we should be able to reach magnitude of 24, 25, or 26.5 in 10 years in the Z band for redshift 0.5, 1, and 2. So this is something that can be useful to have a better idea of what is the environment, and so how this can be related to the evolution also of blazar and radio galaxy in the universe. So to conclude, I think that I've shown that, of course, it's important to put together information at different frequency. And of course, simultaneous observation should be the best, at least for variability studies and to build up detailed SED. But long-term observation with LSST can be very, very important to reveal the nature of variable ecosystem, neutrino production in blazar, also in conjunction with the CTA observation of the most promising candidates. And also not time critical studies like the environment of blazar can be something to be done, and there is a link with what we observe at higher energy for the brightest object. And of course, the discovery of new blazar with LSST will allow to follow up and discover these new TV emitters with the CTA that are more sensible. So we should go deeper and deeper also in the TV sky. And I stop here.
Thank you very much, Filippo. It's very interesting. And thank you for finishing very promptly as well. In fact, slightly early, so we've got plenty of time for questions. I can't see anything in the chat or any hands raised or anything in. Oh, Paolo.
No, just quick. To what extent can you get around the saturation problem by just relying on surveys like ZTF? And there are probably going to be other optical surveys in the south with small telescopes. So don't worry about it, I guess.
Yeah, this is a possible solution in the sense that if you see an increase of the activity of a source up to a certain level, you can follow up with smaller telescopes. And so you can have a continuous, like combining what you have in LST with the smaller telescopes that you have in the southern hemisphere. Yeah.
Thanks.
I can't see any more questions from the audience, so perhaps I can ask one quickly. You sort of touched on this, but perhaps you could be a bit clear about sort of how well matched do you think the depths of CTA and LSST are going to be? Do you expect to detect more blazars in LSST that you don't see with CTA, or do you expect to see more with CTA that are actually missed by LSST?
It's not so easy to estimate. I think that from a raw estimation, we expect to see with LST at least 150 blazars. One relative problem is that in the deep drilling fields, that should be the best field in which you can study variability. There are not so many confirmed blazars, so this reduces the possibility to study blazar with LST with a very good cadence, but there are some candidate blazars that in principle you can study. So I think that with LSST we should see a good amount of blazar. In my opinion, the blazar observed by LSST should be, by CTA should be all detected by LSST, because the usual magnitude, range of magnitude of the blazar observed up to now by energy is well within the limit of LSST, also for a single exposure.
Okay, thank you very much. It sounds lots of exciting science ready to happen. I can't see any more questions, so I think we'll take the break slightly early. We'll reconvene in 11.5 minutes for our next talk, starting promptly at 11:55 New York. Thank you to all of this morning's speakers. Maria Tree. So our first talk this afternoon is from Maria, who's going to be talking about supermassive black hole binaries. Take it away.
Hi, everyone. My name is Maria Harisi. I'm a postdoc at Vanderbilt University. And today I'm going to talk about supermassive black hole binaries, how we can use optical time domain data to detect such systems, and the synergies with gravitational waves from pulsar timing arrays, and how we can combine the two messengers to do multi-messenger studies of binaries. So first of all, supermassive black hole binaries are the natural outcome of galaxy mergers, since every massive galaxy has a supermassive black hole. So the post-merger galaxy will have two supermassive black holes, which progressively lose energy and angular momentum and get to smaller and smaller separations. When they get roughly at parsec separation, the two black holes become gravitationally bound to each other, and they form a binary. Also, because galaxy mergers happen very often in the history of the universe, we expect that we will have many such systems forming in galactic nuclei. Another important thing to keep in mind is that typically in galaxy mergers, we have gas, and that gas will end up at the center of the post-merger galaxy, and it will accrete to the black holes, and that will provide bright electromagnetic emission that allow us to detect these systems. And in terms of where we are observationally, we very often see the very first stages of galaxy mergers and the initial pairing of their black holes. So over the last 20 years, we have seen a few dozens of galaxies that have two active supermassive black holes separated by roughly a kiloparsec. But as we get to smaller and smaller separations, finding these systems becomes very challenging. And in fact, this is the record holding binary at a separation of about 7 parsec that was resolved with a very long baseline interferometry. Below the parsec separation, it becomes very challenging. We don't have the resolution to see the two black holes unless it's a system that is very nearby. And we have no confirmed systems below the parsec separation. So how we detect these systems, we need to infer the presence of a binary from the effect that it has in their environment. and in particular on the gas that I already said should be present around the binary. So the most promising method to find sub-parsec or even milliparsec supermassive black hole binaries is to find quasars with periodic variability. And I would argue that this idea is fairly intuitive, as we have the binary periodically perturbing the matter around it. It should produce periodic variability, but this has also been confirmed in multiple hydrodynamical simulations that look at, they put two black holes in a gaseous disk and they see how it behaves. So what we typically see is that we have initially the binary acts as a propeller, expels the gas from the central region, creates a cavity that has low density gas, but it also pulls a lot of material inwards in these streams that come periodically into the cavity. And we also have matter that is bound to the black holes and is moving around with the black holes. So we have two main methods to produce periodic variability. One is related to these streams that I already mentioned. As they enter the cavity periodically, we have the accretion is periodically modulated, which is shown here. This is the accretion rate as a function of the orbital period, and we see that the accretion rate is periodic with a period similar to the orbital period of the binary. The second is related to the gas that is bound to the black hole. So if we have an unequal mass binary, the smaller black hole, the one that it moves closer to the cavity, it typically has a brighter mini disk. And if it's also close to edge on, we have effects from special relativity. So even if the luminosity is constant here, because this is moving with relativistic velocities, when it's moving towards the observer, it will appear brighter. When it's moving away, it will appear dimmer, and it gives rise to this sinusoidal periodicity. Now, in both cases, we expect that the evolution in the sub-parsec regime to be slow. That means that binaries should spend a lot of times in these separations should be very common. And we should be finding many of those. And in fact, the last 5 years or 7 have been very productive in the search for quasars with periodic variability. Multiple groups have analyzed data from different time domain surveys like Catalina, PTF, PanSTARRS, ZTF, DES, and so on. And now we have about 250 candidates. The emphasis here is on the word candidates because we cannot be sure that these quasars are indeed periodic. It's actually very challenging to find periodicity in quasars for two main reasons. One, the periods we are looking are relatively long. That means we cannot have many repetitions of the periodicity within the baselines that we are looking at. And two, we are all AGN people here. We know that quasars have stochastic variability and that can mimic periodicity. So for example, here, it's the data here are one of the candidates that was identified as a periodic quasar. And the pink here is a simulation of dumb random walk. And you can see that within these data, it's very hard to distinguish the two. So we expect that current samples will have a lot of false detections. And of course, we can either wait long enough to see if the periodicity is persistent, or we can look for multi-wavelength data and look for other signatures. I'm not going to go into this, but you can ask me later if you're curious. And of course, LSST is very exciting for finding quasars with periodic variability, both because the size of AGN that we will detect is very large, and also the quality of the data is better than the current time domain surveys. So there are some theoretical models that predict how many binaries we should expect in LSST. For example, this model by Chin predicts that we should be finding tens of thousands, if not hundreds of thousands of binaries. And the interesting thing is because we have such a big sample, we should expect to find a few of the short period ones, which are more rare. For example, this model predicts that within the single visit limit of LSST, we should be finding a few hundreds of binaries that have a period of 6 months, which means that over the course of the survey, we could see 20 cycles of the periodicity, and then we could be certain that this quasar is periodic, for example. We also have some models that look at the more special case, like the relativistic Doppler boost that I said we need an unequal mass binary at an edge-on orbit that produces the very sinusoidal variability. We should expect about 100 of those. And also, we should expect self-lensing flares. This has been fairly unexplored in the current time domain surveys. The idea is that we have the accretion disk of the smaller black hole goes behind the big black hole, the primary. And we have lensing, and that gives rise to a very symmetric flare. So that's another way we can detect supermassive black hole binaries. So in anticipation of LSST, we were curious to see what signals we will be able to detect and which ones we would be missing. So with Caitlin Witt, who was a student at West Virginia University and will be starting as a postdoc at Northwestern soon, we developed a Bayesian model selection, and we simulated periodic signals on top of dumb random walk and dumb random walk signals. And then we ran our pipeline to see which ones we would detect. So here with red is the detection rate of truly periodic signals as a function of the input parameters, both of the periodic signal and of the dumb random walk noise. And you can see that both are important. So for example, when we have short period binaries, it's relatively easy to find them. When we have long period binaries, it becomes much harder. Similarly, we have strong signals with a high amplitude. Again, it's easy to distinguish them from the noise. It becomes harder when the amplitude of the signal is small. And again, the noise plays a very important role. When we have significant contribution from the dumb random walk, we cannot find the signals. And the other important thing to note is we compared with current time domain surveys, something like Catalina. And the interesting thing here is the false positive rate. So signals that we should not be detecting because they are just dumb random walk. And for current surveys, we have a detection rate which is about 15%. For LSST, this is significantly suppressed to about 3%. So I guess overall we have good news and bad news. The good news is that the false positive rate becomes much lower in LSST from the quality of the data. The bad news is that we are still missing a lot of the signals. So the detection rate is similar to our current capabilities at 60%. The other thing I wanted to mention is that this Bayesian method is relatively slow and cannot be generalized for the entire database. So we need an efficient method to make a first pass of the data and select good candidates that we can validate with this method. Now I'm going to spend a few minutes talking about the other method that we can use to detect supermassive black hole binaries, which is gravitational waves. So these binaries are at the final stage of their evolution, and they're very promising sources of low frequency gravitational waves. The ones I'm going to talk today, they have masses of 10 to the 8 to 10 to the 10. They emit nanohertz gravitational waves, and they're very exciting because we expect that within a few years, maybe within 5 years, we should start detecting these systems with pulsar timing arrays. So I'll spend a couple of minutes reminding you how this method works. So pulsar timing arrays rely on pulsars, on millisecond pulsars, which are magnetized neutron stars, and they are very stable rotators. So we have a beam of radiation along the magnetic axis, and these rotate very stably, and not always the magnetic axis is aligned with the rotation axis. So we have this lighthouse effect. Every time the beam of the radiation passes through our line of sight, we get a pulse that we can record with radio telescopes. And this repeats very stably, and we get many repeating pulses within a second. Now, if we have gravitational waves passing through our own galaxy, they will affect the pulsars that we observe. They will squeeze and stretch the space-time. So some of the pulses will have to travel a longer distance, some will have to travel a shorter distance. So some of them will arrive sooner than expected or later than expected. And if we see this signal across many pulsars, we can detect gravitational waves. So why is this exciting for us here in LSST? This is very exciting because practically with pulsar timing arrays and the method I was describing with quasar periodicity, we can probe the same population of binaries, roughly the same masses, the same periods, and so on. So it makes sense to put the two data sets together. And for example, here I'm showing a simulated signal of the supermassive black hole binary. This is how it would look in pulsar timing array data. And this is the respective Doppler boost emission in electromagnetic data. And you can see we can connect the two signals. The frequency of the gravitational wave is twice that of the electromagnetic wave, but otherwise we can put them together. And we explored how many of these systems would be detectable with both methods in terms of the binary parameters, for example, the total mass or the period. So starting from a relatively edge-on binary here and going to higher, to more inclined binaries, this is the blue shaded region is the one we could detect in electromagnetic waves. And the purple shaded region is what we could detect with gravitational waves, current capabilities, what we expect to have when LSST starts, and what we expect to have when towards the end of LSST. So now we are limited at the most massive supermassive black hole binaries. They have to be almost 10 to the 10. But as the sensitivity of pulsar timing arrays increases, we will have more and more binaries where we can do joint multi-messenger observations. So we started developing a pipeline that will put together optical time domain data and pulsar timing array data. The idea here is that, for example, we have different dependencies on the signal. So here I'm showing the mass ratio versus the total mass of the binary. And with orange are the constraints we would have if we had electromagnetic data only. Blue are the constraints we would have only with gravitational wave data. And you can see that putting them together, we get better constraints. So this is, yeah, I'm almost done. So this is under development right now, but the preliminary results we have are very encouraging. We get better parameter estimation, and in some cases, we also get a boost in the detectability for gravitational waves. So just by having electromagnetic candidates and putting them together with the gravitational waves, we may get to the detection of gravitational waves faster. And I will just briefly give you the takeaway points of this talk. So supermassive black hole binaries should be common as a result of galaxy mergers. They can be detected as quasars with periodic variability using time domain data. And in fact, we now have about 250 candidates. It's relatively hard to confirm whether these candidates are truly periodic. And the good news is that LSST, with the quality of data that we will have, will provide reliable candidates. So it will minimize the false detection rate. These sources are also promising sources for gravitational waves. We think that in the next 5 years, we should start detecting these systems, and we can start putting together optical time domain data from LSST and pulsar timing array data, especially because we can probe very similar binaries. And as the sensitivity of pulsar timing arrays increases, the population of binaries we can probe with both methods will increase. So thank you.
Thank you very much, Maria, for the nice talk. And Niel has a question.
Yeah, thank you for the nice talk. I remember, because I don't work in this field, but I read papers as they go by on archive, not carefully, but I remember that, about this quasar PG1302 or whatever, there was a lot of debate about the true level of significance, for the system. And, and then I know there's been further data from Assassin, and people write papers about did Assassin kill this one or not. I can't follow, but my question, I guess, is, has the broad supermassive black hole binaries community agreed upon a robust detection methodology that's going to be used so that you won't have some people publishing one thing and other people publishing other things, and they disagree, and it's just going to be total chaos? Has the community agreed that you have to have a certain number of cycles, or you have to perform a certain type of simulation so that you're convinced things are actually correct?
So I would say for this candidate, the PG1302, the jury is still out. I think the longer data will actually tell us whether it's periodic or not. In general, the consensus is that the dumb random walk, or the stochastic variability in general, is very important and can introduce false detections. This was sort of our motivation here to see what level of false detections or what level of missing signals we will have. And I think you're right, we have not converged on what is the minimum number of cycles we should observe to have robust detections. It seems that what we have now, which is 1.5, 2 cycles, maybe not enough, but I would say because we don't have any other candidate, we don't have any confirmed binaries, just finding the most promising sources and then start filtering them out, that would be my approach. Maybe not extreme cautious that would not allow us to find any of the binaries, but have some false positives in there and then filter them out with additional data.
Okay, thank you.
Thanks. Bojana?
Just a comment about question. I think people like Simon Vaughan or Alex Markowitz would say 4 periods. That guarantees you that you see the periodicity. But actually, I have a question about those binaries which may be seen in LSST. If the period is short, would you see any departure in SED, for example, the signature of smaller outer radius or something like that, which could then support your claim of periodicity or, well, this binary system?
So are you thinking of maybe these mini disks will be truncated?
Exactly, yes. Would you see that in SED?
So there are predictions of what you would see in quasar SED, but I would say they're not, the simulations have not converged to a signal picture. So people expect that you will see a deficit of light, maybe in optical UV, because you have this part of the disk that is missing. Some people expect that you will see an excess of light because you have the shocks. So I think the theories have not converged on what is the signature on the SED.
Okay, thank you.
So now in terms of what you mentioned about the periods, I agree that if we rely only on electromagnetic data, maybe having more periods helps to have more robust detections. But my suggestion here is that we can also have another messenger. So we have a candidate and we have an indication from the same binary, from the same part of the sky, that we have a binary with the same frequency in gravitational waves. So in that case, I would be more relaxed about allowing longer period binaries and looking at the gravitational wave data.
Yeah, I certainly hope that would indeed help. Yeah.
Yes.
Seb has a question, if you can keep it quick.
Yes. Okay. So question is, how sure are we about the expected amplitudes here? I mean, is what you modeled realistic or not?
The expected
Are we-
amplitudes of the AM
yeah.
signal?
So are we kind of at the moment looking for the right amplitude, or should they be much smaller, for example? I mean, I'm looking at, for example, QPOs in X-ray binaries where the amplitude, kind of the contrast is really low, and so.
Right, so it depends on which model we are thinking. So with the relativistic Doppler boost, if we assume a mass ratio and the mass of the binary, we can predict the amplitude. When it comes to periodic accretion, I would say here the amplitude is much more uncertain. And the reason is we don't have radiative feedback in the simulations, so the periodic accretion rate cannot be quite translated into flux periodicity. So yes, this is more robust. We can predict the amplitudes very well with almost no assumptions. This is more speculative, let's say, or uncertain.
Okay, thank you very much. We should move on. So Lorena, if you can start sharing your screen. Maria, I do have a quick question for you, but I'll put it in the chat. So our next speaker is Lorena Hernandez Garcia, who's going to be talking about the LSST broker. And it's services for AGN science. So Lorena, when you're ready.
Thank you. Hi, everyone. I'm Lorena Hernandez Garcia, and I will be speaking on behalf of the LSST broker, which means automatic learning for the rapid classification of events. And the idea of this talk is to give updates on the services provided by this broker and to focus it on AGN science. So with the idea of helping you with your science. So these are services that you can use and that will be available when the beta Rubin starts working. So let's start speaking about brokers. So when the beta Rubin starts working, the way in which this will work is that we will have the beta Rubin or maybe other Savic telescopes that might work the same. And the community brokers will be responsible for ingesting the alert stream and to send it to downstream brokers and also for target and observation management, as well as to help deciding what are the interesting sources to be followed up by other telescopes, as well as to send this information for the user community. So there are 7 different brokers, which you can see in this map. 6 of them are located in the Northern Hemisphere, and there is one which is LSST that is located in Chile. So if you're still asking what is exactly a broker, then I have to say that the definition is unclear, and this depends. Well, there is a minimum service that the broker will give to the community, but then it depends on what the brokers decide to do. So it could be a system for filtering or classifying the alert stream, or it could be a system for annotating the alert stream by, for example, cross-matching with different catalogs. So instead of focusing on the definition of a broker, I prefer to focus on what are the needs of the community, and this might help the brokers to decide what products and services to offer. So during the broker workshop in 2020, we did this table that you can see here. So these are the 8 different sciences collaborations for the LSST. And these are the different services these are some of the services that can be provided. And what we did was to watch all the talks and to see what are the requirements from all of them. So in particular, this is the AGN science collaboration, and these are the services that we thought were important for the collaboration. So it's cross-match, MARSAR, watchlist, classification, feature, and data release. So I take this opportunity to ask if these are still requirements for the science collaboration, and any feedback from you, maybe in this moment and maybe in the future, is very welcome. And this might help us and also other brokers to develop the best services. So here I saw some of the services that can offer brokers. So maybe you can take a look at them and let us know. As I mentioned, different brokers can offer different services. And now let me focus on the LSST broker. As I said, this is a broker located in Chile, and this is an initiative to build a community broker for the Vera Rubin as well as for other 10U survey telescopes. I think being in Chile might be an advantage because Vera Rubin will also be located in Chile. And well, right now, LSST is ingesting the CTF alert stream since 2019. So because this is an all sky survey, then the scientific questions are focused on different science cases, as you can see here. But now let's focus on what is related to AGN. And from now, I want to show you the services that are already available and are using CTF data to, we're using CTF data to develop these services and that you can use. So in LSST, we have two different classifiers based on machine learning. Indeed, LSST was the first broker in introducing classifiers. So one is the stamp-based classifier, which uses images like the science, the reference, and the difference image with convolutional neural networks to classify sources into 5 different groups, including AGN. And then there is a light curve-based classifier, which uses the light curves. In this case, it needs at least 6 detections. And using a balanced hierarchical random forest, it allows to classify the sources into 15 different classes. These two are the confusion matrices for the two classifiers. And from the light curve classifier, we can define the actual LSST taxonomy, which you can see in this figure. So these are the 15 classes that can be classified, and among them, there are 3 classes of AGN, which are Blazar, Quasar, and AGN. Then there are different ways to explore the data. Maybe the easiest one is the LSST Explorer. You can access it in this website. And here's a video that can show a little bit how to interact with this interface. So you can select different classifiers and the different classes. In this example, we will see the example of blazars. We search them and we get a list of them with different columns and, for example, the probabilities. And then if we click on any of them, we can see the light curves in the G and the R filter. We can also display the data release. I will talk about this in a minute. And well, then we can have some different information, basic information with the statistics, the classification using these classifiers, as well as the stamps and the image from Aladdin. And we can also do cross-match with different catalogs and different radius. For example, here, if you go to net, you can check, for example, the redshift. And well, we can, if you see in the left, there are different light curves for different sources. So what is displayed here is different light curves for different blazar candidates. Then there is, as I mentioned, the light curve classifier. The way in which it works is from calculating features. So in LSST, 174 features are calculated per light curve, and the library to estimate to calculate these features is available in GitHub and explained in this paper by Paula Sanchez Saez. And well, for example, here I saw the top 5 features per hierarchical level. And you can see, for example, in the case of stochastic, where AGN are located, we can see that colors are quite important. Here we have colors from WISE or colors from CTF. And in fact, this library is useful not only for CTF data, but for any light curve in any wavelength. So this is also something that can be used and is very useful for variability analysis. Then, as I mentioned before, we have integrated the data release in the Explorer. And well, I want to show this with an example. This is the light curve from the alerts in the GNR band, and here we have the data release. So it means that we have all the information. So in blue and in gray, we have the data from the data release, and the green and red are only from the alerts. So this is very useful, and in fact, it has been very useful for us in order to detect outliers, because this way we have all the information. And also for people who work with supernova and send candidates to TNS, this is also very useful because they can check whether there was previous activity or not before sending the candidates. Another service is the watch list. So this is useful in case you have a sample of your preference with your favorite targets, and you want to cross-match them in real time and get notifications by email. Then this is probably your service. So very brief. Let me start again. So here you can upload your sample in a CSV file. You can see how to do that, and then you can see if there have been matches with if there have been new alerts, and you can also access the Explorer, and also you can set what frequency do you want to receive your emails. So this is good if you have a large sample of sources, for example, and you want to see whether they have new detections or not. There are also different Jupyter notebooks available in GitHub and focused on different things. So there is one notebook to work with the client. Then there are some science cases. One of them is focused on AGN. There are another two notebooks to use the classifiers, the light curve and the stamp, and some other notebooks that might be helpful for some people. For example, there's one with the watch list and another one with galaxies using pan-stars. So in these notebooks, you will be able to learn how to interact with the API and the client. And here we have one API for the alerts and one for the data release. And the installation of the client is quite easy. You can use pip. These are examples of the notebook for using AGN. So in the left we have the access for the client, and in the right we have a direct access to the database. So probably the difference to use this is the number of sources that you want to access. So if you want some thousand of objects, it is better to use the client. And if you want a large sample of sources, then it will be better to use the database. In any case, both are well explained in the notebook. So if you want to use it, you are very welcome. Now I want to show, so these are the services that are already available and work with CTF data, and this will be available when the Vera Rubin starts working, maybe with some differences. And now I want to show you some things that are under development. So one of them is the anomaly detection. So one of the important things that will come from Rubin is the ability to recognize outliers, because this will be interesting sources or even new sources. We submitted a paper recently, and for example, here is one of the sources. Well, we applied this to real data. I think this is quite extraordinary. And for example, this is a source that was classified by the Lightbulb Classifier as a blazar, and in the end we found that it was a very interesting star. And another thing that we are working on is in building a multi-stream broker by including not only data from the CTF, but also from Atlas. This is in production now, so we are doing the tests. For example, here I saw a light curve of an AGN. Indeed, this is a binary black hole candidate. Here are the stamps, and in red and green we have the light curve from CTF, and in orange and blue we have the data from Atlas. So one thing is that Atlas has data since 2015, and the cadence is smaller, so we have more data points. So so this might be also interesting. So as I said, we are testing this, and if anyone is interested in working with Atlas data, you can speak with us. and we can see if we can give you access to work with this data. The idea is that in the future, this will be public. And to finish, I want to show you some examples of science that has been done with Alerce, or things that we are working on to do science. So one is this paper led by Paula Sanchez-Saez, where we used variational autoencoders to select changing state candidates in massive data sets. This is in the left, we can see the architecture of these variational autoencoders. And so the idea is here that in the input, we have the light curves, which are the black points in the right. And then it goes to the encoder, the limited space, the decoder, and the output is a prediction, which is plotted in red. And then to select the sources, the RMS gives an idea of what of them are the candidates. If I remember well, it's an RMS of 3 that make a selection for the sources. Another paper that was published recently is this one led by Elena Lopez Navas, where we used sources selected as type 2 AGN in catalogs such as Miliquas. And we found that and we selected those that were varying in the CTF alert stream. From the sample, we selected 6 that were observable with SOAR and compared the spectra with archival SLOAN data. And these are from those 6, these 4 that I saw here, so broad lines in the spectra from SOAR. So we can classify them as changing look AGN. So as you can see, Alerce is good to select sources through variability. And indeed, this is something that has been done for foremost, in particular in this. Okay, thank you. In this team, in the change team, which is led by Franz Bauer and Paulina Lira, where the selection of the sources, or part of the selection of the sources, is being done using variability from Alerce, or from CTF. And Alerce can also be useful when we have data from different well, we have the light course in multi-wavelength data. This is an example of a giant radio galaxy that has a blazar-like nucleus. And in particular for this work, it was very useful to have the feature calculator that I saw before, because here we have data from radio to X-rays. For example, these are the light curve from CTF and Atlas. So we were able to estimate the many features, as well as to compare the optical variability features of large samples of AGN and blazars, and to compare the variability properties of this source, and found that it actually behaves more as a blazar than as an AGN. And this to confirm that, in fact, there is a blazar nucleus in a giant radio galaxy. And just to finish, I want to leave you with this, with links to, well, with useful links. So, well, I have here the presentations of the publications of Alerce, and then these links. So this is the general website. Here you can find all the information about Alerce as well as the services. This is the Explorer, the watch list, the notebooks, and then there is this one, which are a link for the workshops, and here you will find, for example, tutorials for the notebooks. So I hope this is useful for any of you. If you have any comments or feedback, that is very welcome. Thank you so much.
Thank you very much, Lorena. What questions do we have? Okay, perhaps I can kick one off then. Are you worried at all about scaling up to LSST data volumes? I mean, I know CTF is already a large volume, but LSST is going to be a couple of orders of magnitude bigger. do you foresee any challenges with transitioning to LSST era?
We're working on that. Indeed, for example, Atlas has a much larger volume of data. And right now we're also working with Elastic, for example, which is something more similar to LSST. But yeah, we are dealing with that.
Okay, thank you. And there's a comment from Franz in the chat. I don't know if Franz wants to speak himself, or I can read it out.
Not really, just to add that, you know, if there's something you guys don't see that you would like implemented, that would be useful to know. We don't guarantee that we will be able to implement it, but right, if you can expand on our use cases and you know, let us know if there are things that appear to be missing or are not useful. Obviously, that's useful feedback for us.
Yep.
Niel?
Yeah, just perhaps related to that, I did want to ask, does LSST have long-term stable funding so that this will be solidly continuing for the full 10 years of Rubin? I know that clearly it's a challenge to keep these big projects going when you have a marching army that has to keep going for a decade. And I just want, for example, has the Chilean government committed to doing this, or what's the situation there?
So the short answer is hopefully, and maybe Franz can add something more on that.
Yeah, so I mean, we built this thing on a 10-year institute funding, and that's dwindling down in the last 1.5 years, and we're having meetings now about how to postulate for another 10 years. So at the moment, Neil, no, we don't have a guaranteed 10 years of funding. Hopefully, and we can come back in a year and say, yes, we do. But yeah, that's where we're at.
Okay, thanks, Franz. Paolo?
Yeah, one question, discussion I had with other brokers was, how big a watch list will you guys allow? Like I talked to Lazare, we had talked about having like 4 million AGN that could be monitored with various criteria. Is such a watch list too large, or do you see that becoming a capability?
I think right now it's about 10,000 sources, something like that. So 1 million, I think, is too much right now. And also because right now we don't have filters, so probably it's not so useful. So maybe if you want to add filters, this is something that you should ask to LSST, because in LSST we are many people and there are different things that needs to be worked. So if this is something interesting for the science collaborations to add filters to the watch list, then maybe you should send a requirement for LSST, or if you want, I can also give this message to LSST. But right now, as the watch list is working, is that if you put 1 million of sources, well, which is not possible, but let's say you put 10,000 sources, then you will receive a large email with a lot of alerts, because all of your sources, which are, because you have your reference, and this is not like a supernova that when there is a new alert, this is something new because you have your reference, and when the flux increases or not, then you received an alert, and maybe it's not something interesting. And the idea from the watch list is to get something interesting. So I think right now it's better to upload samples of sources that are interesting in a way, or that you can check.
Okay, thanks. And one other question, will you be including like the ZTF data releases in LSST so you can get a extended light curve, or are you just archiving the alert data?
This is already included in the Explorer. So if you go in the Explorer, then there is a button that says data release. You click there and you get all the light curve.
Okay, thanks.
Okay, thanks, Paolo. There's a question from Dragano in the chat. Thanks for the great presentation. My internet is poor, so I may have missed this. Can we access LSST alerts through Tom Toolkit?
So LSST is connected to the TOM toolkit, but I'm not sure if anyone can send the information. I mean, I don't know if I don't think it's possible right now to observe in other telescopes. But this is something that would be great in the future.
Okay, thank you. And perhaps if Dragana has follow-up, she can use the chat for that, and we can move on. So our final talk today is from Priyanjali. If you can start showing your screen.
Can you see my slide?
Yes. So yes, Priyanjali, we're talking about AGN variability as a function of rest frame wavelength.
Yes. So first of all, I want to thank you all the organizers for inviting me. So the title of my talk is the variance as function of rest frame wavelength. Also, I would like to thank you, my professors, for their guidance. So here we perform series of investigations to understand the mechanism behind the AGN variability. So first we study the variance as a function of black hole mass and Eddington ratio. And the work that I will be presenting here, this is the study about the AGN variability as a function of rest frame wavelength on different time scales. So these correlations can be used to obtain the AGN physical characteristics and accretion disk model constraints. So in this way, we can characterize the huge sample of the LSST survey. Also, this ZTF survey is designed to support as a stepping stone for LSST in study of variable objects. Here, this is the table to compare the ZTF survey with the LSST. So here, as you can see in the table, the number of total sources and the total detection in the ZTF survey is significant as compared to the LSST survey. Also, the magnetic depth in ZTF is about 20.5 for the R band, while this is 24.7 for LSST survey. Also, ZTF survey has 3 filters and the LSST will have 6 filters. Although this ZTF survey is not as huge as the LSST survey, but this can be used for the predictions. So here first I will be giving you the introduction of a study, then I will move to the project and current results. After that, I will briefly explain how this project can be extended for the LSST. So here this study is to explore how the AGN variability is correlated with the rest frame wavelength, and here this is the cartoon to explain the temperature profile of the accretion disk. In the center, this is the black hole, and around this this is the accretion disk, which is made up of different annuli, and the assumption is that this annuli of the accretion disk emit the black body radiation. So when the matter comes closer to the black hole, we get the higher amount of luminosity closer to the black hole. Also, if we plot a power spectral density for the G band and for the R band, so we expect a higher amount of normalization for the G band. There are some models to explain the AGN variability. Here I will mention about 2 models. The first one is the reprocessing model. So in the center, this is black hole. Above this is the corona that is shown by the orange, and the accretion disk is shown by the blue part. So the corona emits the X-ray, and this X-ray get absorbed by the accretion disk, which reprocess it from UV to the infrared. Although this reprocessing model is able to explain the temperature profile of the accretion disk and some other observational facts, there are some limitations of this model, and one of the limitation is that according to this model, there should be a tight correlation between the different wavelengths, between the variability of different wavelengths. So we do not find a tight correlation in the observed data. So there is another model, that is corona heated accretion disk reprocessing model, which can overcome this limitation. So on the right, this is the car model where the accretion disk is shown by the gray and the corona is in the light blue. And according to this model, the corona and the accretion disk are magnetically coupled. So here the magnetic fluctuations is it drives the X-ray in the corona, and this magnetic fluctuation propagates to the accretion disk, which change the heating rate, and after that it induces the temperature fluctuation. So there have been previous studies that have reported the anti-correlation between amplitude of variability and rest frame wavelength. So on the right, this is the plot of long-term structure function as a function of rest frame wavelength. And here the different contours represent the different filters, and this red line is the median power law that is fitted from left to right. So in this study, we are using the CTF data release 6 light curves, where the light curves has a 3-night cadence and the baseline is of 3 years length with the yearly gaps. So on the top, this is the G band light curve. Below this is the R band light curve from CTF. Also, we need to define a good sample for our study, and for this we selected the sample using the catalog of the Rakshit, where they did a homogeneous study of the SDSS data release 14 quasars, and they reported black hole mass Eddington ratio and redshift among other physical parameters. So the sample covers the redshift range from 0.1 to 0.8. Also, in this sample, the black hole mass has been estimated using the H-beta line, which is the best mass estimator. So our final sample contains 3,429 light curves in the G band and 3,897 light curves in the R band. And after extracting the light curves for the final sample, we estimated the variance, where variance can be defined as a measure of variability amplitude. On the left, this is the power spectral density of the AGN, where broken power law can describe the AGN variability. So in the region 3 and region 2, the AGN follows the red noise. So this PHT can be described as 1 by f power alpha, where f is the frequency. So when we plot the variance values as a function of time scale, we can obtain the power spectrum. And for this project, we are calculating the variance by using the Mexican head filter, which is able to calculate the variance for the uneven sampling data. So sorry, for uneven sampling light curves. After this, after estimating the variance, we make the sample homogeneous. So here you can see on the right, this is the histogram of the black hole mass on the top, and below that this is the histogram of the Eddington ratio. So since this sample covers a certain range of black hole mass and Eddington ratio, we scale the variance with the black hole mass of 10 to the power 8 solar mass and Eddington ratio of 10 to the power -1 by using the table from the Arevalo et al. 2022. So after making the sample homogeneous, our study aims to find the correlation between the variability as a function of rest frame wavelength And for this, we use the redshift as a tool to study the different rest frame wavelength, where we obtain the rest frame by dividing the bandpass filter to the 1 plus redshift. So on the left, this is the plot of the variance versus rest frame wavelength for the time scale of 300 days. And here we group the variance for the quasars into 17 bands of rest frame wavelength, where each value represent the median value. So here in this figure, we find the decreasing trend of the variance with the increasing rest frame wavelength. Also, we did this analysis for the time scale of 75 days, and we find the anti-correlation. And in addition to that, we find another result, that is the slope is steeper for the time scale of 75 days for this plot variance versus rest frame wavelength as compared to the time scale of the 300 days. So after finding this result, we compare a result from the ZTF data with the car model that I mentioned before. So here, this is the plot of the variance versus rest frame wavelength, where these black data points are the variance from the ZTF data, and in the blue, these are the points from the car model, where we simulated the light curves from ZTF data using the car model. And after comparing this, we find that the slope agrees with 1 sigma precision. And when we did this comparison for the time scale of 75 days, in this case also, the slope agrees with 1 sigma precision. So after this, if we go back to this figure, that is of variance versus rest frame wavelength, there are some wiggles in this plot. For example, around 3.55, there is a peak in the variance. And to understand what causes this peak around this point, we overplot the template of the spectrum on the top of the plot of variance versus rest frame wavelength. So here there are different different template of the spectrum. So if you see around 2800 and around 4800, there is a suppression of the variance